Boys and girls, on this beautiful Friday, the weather is allowing, and I hope that you are ready for me again. If you don't know me, my name is Mr. Sibanyoni, and I'll be taking you again for Technical Sciences Grade 12, and we are continuing with momentum and impulse. Remember, my dear learners, the purpose of the lessons at the moment on this particular topic is to really give you insight and to make sure that you are able to answer exam type of questions. So even yesterday we were doing questions from previous examination papers from different provinces as well. So even today we are going to do the same thing, and it will help us to really up our game so that we are able to obtain the level 7s that we want. So we continue in the overview of the lesson basically, and the same as the features of the topic, we will be doing questions on momentum and impulse, as well as the assignment. And for those that are new again, I will be reminding you of what you need to take care of in terms of preparing for your examination, right? We shoot straight into the questions on momentum and impulse. This question is from the Gauteng Department of Education for their trial examination in 2019 paper 1. So it is a nice question because it really addresses quite a number of things that you need to understand in this particular topic. Okay, just waiting for my pen to work with me here. But as it tries to, I'll read the question for you. It reads as follows. 2 train coaches, A and B, with masses of 1,000 kilograms and 2,000 kilograms respectively, are attached to each other with a compressed spring. They move to the right at 4 meters per second along a frictionless horizontal railway track. When the spring is released and it has expanded completely, the 2,000 kilogram coach moves to the right at a velocity of 5.6 meters per second, as shown in the diagram below. So what are we seeing here? Number one, we have the 2 coaches A and B, and that A has a mass of 1,000 kilograms and B has a mass of 2,000 kilograms, right? And they are moving to the right at 4 meters per second. In other words, both of them are moving at 4 meters per second along a frictionless horizontal railway track. Remember what that means. Immediately when we are told that there is no friction, then we understand that the system is isolated, right? The system is isolated because they have just told us that the railway track is frictionless. Now, when the spring is released, right, this compressed string, when it is released and it has completely expanded, then the 2,000 coach then moves to the right at the velocity of 5.6 meters per second, as shown in the diagram below. In other words, we do not know the magnitude of A after the explosion. So this is a typical example of an explosion. It's not really a collision, it's more of an explosion more than anything. And as a result, you then know that you need to be able to work with explosions as well altogether. Now, when you check here, before the explosion, remember this side represents before the explosion, and then this side represents after the explosion. Now, before the explosion, they were moving together. In other words, the initial velocity of A and the initial velocity of B is definitely 4 meters per second. And then after the explosion, right, you will see that A has separated from B and they are moving in completely as two different objects, and they are no longer a system like before, and therefore each will have its own velocity. Then for 3.1, we are required to state the principle of conservation of linear momentum in weights. By now we know, my dear learners, that the total linear momentum in an isolated system remains constant in magnitude and direction. So the total linear momentum in an isolated system remains constant in magnitude and direction. Another learner could have said the total linear momentum of an isolated system is conserved in magnitude and direction. So for that, we will definitely allocate 2 marks. And to mark it, we do exactly that. The total linear momentum of an isolated system remains constant in magnitude and direction. You should be able to see there that it's 2 marks or nothing. It means it's not part marking. So everything definitely has to be correct in order for you to obtain the 2 marks. It means you can't get a 1 out of 2. So we know for others, instead of saying remains constant, then they will write it is conserved. So it is solely up to you altogether. Right. Let us go to the next question. Now, we are required to calculate the magnitude and direction of the velocity of the 1,000 kilogram coach immediately after the spring has expanded completely. In other words, after the explosion altogether. So we want to know what is the speed of this particular coach. Are we clear? Right. And which speed are we looking for? We are looking for the speed when this particular coach has actually when the spring has actually expanded altogether. Now, for us to be able to get this particular for us to be able to actually get this particular velocity after the spring has completely expanded, then we need to apply the principle of conservation of linear momentum altogether. We need to use the principle of conservation of linear momentum, and we know we can apply it because they told us that it is frictionless altogether. Then how do we go about that particular question? And there is something that I also want you to be able to see there, that sometimes because you get marking guidelines, I want you to also be able to interrogate it and not just take things as they are altogether. Right. Let us go and see how we calculate that. Are we clear? Right. So the sum of the momentum before the explosion is equal to the sum of the momentum after the explosion. Then, because before the explosion, they were moving together, they were one system, it means this part there, the initial velocity is the same, so I can take it out as a common factor. Now, if it is a common factor, it means in brackets, then I will have the mass of coach 1 and the mass of coach 2 altogether. Now, this still means the same thing because it's mass times velocity, so it gives you the product of the mass and the velocity, which is the momentum of coach number 1. And then again, it's the mass multiplied by the initial velocity, which then gives you the product of mass and velocity, which is the momentum of coach number 2. Altogether, my dear learners. Now, that is before the expansion, before the explosion, and it will be equal to the momentum of coach 1 after the explosion and the momentum of coach 2 after the explosion. Now, when you go to your diagram, what you should be able to see there is that our coach 1 is the coach that we refer to as coach A, and our coach 2 is the coach that we refer to as coach B. In other words, my dear learners, I know that some of you are going to prepare in your respective provinces. For example, learners in Gauteng, you most probably have access to these questions and marking guidelines, and you see something like this and you become a little bit surprised. How? Because there, if you actually check, the mass of coach A is 1,000 and the mass of coach 2 is 2,000. In other words, the mass there, it's not 2,000, but it is in fact 3,000 when you add them, because it's 1,000 plus 2,000 multiplied by 4 altogether. Then you go to the other side, it's 1,000, the mass, this is now after the explosion. So it's 1,000 multiplied by the final velocity of coach A, which is what we are looking for. And remember, we don't give it direction. And why are we not giving it direction? Because the algebra will work it out. You are still solving for that altogether, my dear learners. So you can't give it direction. Then we say, okay, we leave it as VF1 plus the momentum of coach B, its mass is 2,000, and after the collision, it was going to the right. And basically there, it just means that we chose to the right as positive. So we'll substitute the 5.6 meters per second as a positive value altogether. Right. Then you do your mathematics. If you do your mathematics, this side, you are going to get 3,000, which you will then multiply by 4. Then this side you will get 1,000 VF1, and then the other side it will be 2,000 multiplied by 5.6, which then gives you 11,200. Then if you bring the 11,200 this side and you subtract it from the 12,000, then it means you will be left with 800. Then if you are left there with 800, it means basically you will be left with, let me just put it there for you. The next step will be 800 is equal to 1,000 VF. Then you work out the VF. For you to get the VF, remember you need to divide both sides with 1,000. And if you divide both sides with 1,000, then you will find that your answer is 800 divided by 1,000, and that definitely gives you 0.8 meters per second altogether. Now remember, my dear learners, this value is positive, right? So that value again, it is also positive. Now, when you work out the answer here, you actually get a value that is positive. Why are you getting a value that is positive? Because this product gives you 12,000. This product gives you 11,200. So when you bring it to the other side, you actually get 800, and that 800 is positive. In other words, when you are getting a positive 0.8 meters per second, then you are required to interpret it. And when you interpret it, then it will give you VF to actually be 0.8, and this will be meters per second. But remember what positive means. The positive still means to the right. In other words, there, my dear learners, our answer must be to the right. Now, what is the lesson here? When you get a question paper and maybe you want to check yourself with the marking guidelines, also be able to check yourself and see if there is perhaps not, a mistake. But if you just take things as they are and you are not actually, interrogating them as you are doing the process of learning, then it will give you a challenge, because now you end up being confused. So to really just go back to this one and clarify it for you, remember the mass of Coach A was 1,000 and that of Coach 2 was 2,000. So it gives you 3,000. And remember, they were going to the right. And if we choose the right as positive, so that will be a positive 4. It will be equal to, after the spring has expanded, it's 1,000 multiplied by the final velocity of that, which is what we are looking for. So we don't give it direction, plus the mass of Coach 2, which is Coach B, is 2,000, and it was still going to the right at a velocity of 5.6 meters per second, hence it was positive. You work out this, it gives you 800 is equal to 1,000 VF. Then you get VF, it's a positive value. In other words, when you go to interpret it, then it will give you 0.8 meters per second to the right. So I hope that you were able to see that one. Are we together? Just trying to get to my slide there. Good. So we are done with that question and it gives us 4 marks. So now we continue. Then they tell us if it takes 0.2 seconds, right, for the spring to expand completely, calculate the impulse of Coach A on Coach B. So the impulse must be on Coach B. Now we've been given the time there, and we know that time represents my delta T. It is the contact time. It is the time the net force was acting on that particular coach, which is both Coach A as well as Coach B. So now we must calculate the impulse of Coach A on Coach B. Remember, my dear learners, we want impulse. So impulse is a vector quantity. So it has both magnitude and direction. So it means when we go and give the impulse here, we can't just give the magnitude. We also have to give the direction. And it must be the impulse that is acting on Coach B. It means we will use information of Coach B. So I hope that one is very clear, right? Let us go to that one. Impulse, we know it is equal to the change in momentum. And we know impulse, in essence, we say it is F net delta T, and we know very well it is equal to delta P. And hence, when they go further, they can just say then F net delta T is actually our impulse, which is equal to the change in momentum. And my advice is always start with that formula, because this is the one that we give you in your formula sheet. Then you can tell them that F net delta T is actually impulse, which is equal to the change in momentum. And that will be MVF minus MVI. Because you know when you see delta P, you see MVF minus MVI. Then the mass is 2,000 into the final velocity, my dear learners. Remember, it was 5.6 meters per second, and it was going to the right, and the right is positive. So there we put 5.6 minus the initial velocity is 4 meters per second. Remember, this is the velocity before the spring expanded, the velocity before the explosion, and hence the minus this from the formula, and the velocity is substituted as a positive value because it was going to the right. Then you do your mathematics there. Remember now, when you do your mathematics, you will say 2000 multiplied. In fact, you can just work out the brackets first, right? So if you work out the bracket first, it means what you are going to do is you will say 5.6 minus 4. Then the learner will say, okay, that is going to give me 1.6, and then you take the 1.6 and you multiply by 2000, and when you multiply by 2000, then you see your answer will give you 3200 kilograms dot meter per second. Now, what I want you to also realize there, my dear learners, is that we were looking for the impulse, and impulse is a vector quantity. So direction is actually not indicated there. So that is just an omission. So basically there, I'm expecting you to include to the right. Why is it to the right? Because our value is a positive value. So the actual full mark there is for the answer together with the direction, because we were not asked for the magnitude of the impulse, we were asked to calculate the impulse. So we need to give both magnitude as well as direction. So that was quite an easy one altogether, right? Then someone could have said, Minero, what if I wanted to just use the product of the net force and delta T and to get the impulse altogether? Meaning a learner would say, what if I said impulse is equal to F net delta T? Then we could say, okay, we have the contact time, it's fine, but the problem is we do not have the F net, and hence we calculated the impulse using the change in momentum. Then we go to the next question. Calculate the average force exerted by coach A on coach B. So we want to know the force that is exerted by A on B. So we want to know the force that is acting on coach B. It is exerted by A, but it is acting on B. And hence we are going to substitute values for what? For B, because we want to also get the correct direction for the average force. Then we go to our formula then. F net delta T is equal to delta P, we get 1 mark. F net multiplied by 0.2, yes, because that is our contact time, we get 1 mark, is equal to, remember, impulse is equal to the change in momentum. So this is the impulse on coach B. So if this is the impulse on coach B, it means this is the change in momentum on coach B, and hence I will substitute it there. And the change in momentum, it's a vector again, so I substitute it with direction, and the direction is a positive, and hence it is just positive 3,200. So you don't substitute it without considering direction. The change in momentum must be substituted considering direction because it is a vector quantity. And I see that the F net is going to be equal to 16,000 newtons altogether. And this 16,000 newtons is the magnitude of the net force. But I'm expecting the learners there to then include to the right. Why must you include to the right? You have to include to the right because We were asked to actually calculate the average force. We were not asked to calculate the magnitude of the average force. So there, my dear learners, we actually have an omission. The full mark is for 16,000 newtons, and that is definitely to the right. And that will then give us 4 marks. Then we go to the next question. How will the average force exerted by A on B be affected if the time taken for the spring to expand is increased to 0.5 seconds? Write down only increase, decrease, or remains the same. Then in the subsequent question, we are expected to explain our answer to question 3.4.1. Now remember, my dear learners, when you take that formula, F net delta T is equal to delta P. If you rearrange this formula and say F net is equal to delta P over delta T, so it's still the same formula, just rearrange. Then we can see the relationship between F net as well as delta T. And the relationship that we can see here is that they are inversely proportional. Now, if they're inversely proportional, what does that mean? It means if you increase the contact time, then the net force is going to decrease. If you decrease the contact time, then the net force is going to increase altogether. So what have we done here? We have increased the contact time to 0.5 seconds. Remember, it was 0.2. In other words, if we increase the contact time, then the net force is going to decrease. So our answer there is purely to say the net force is going to decrease. And we were required to give a reason for that. And we say F net is inversely proportional to the contact time as per that particular formula. And that carries 2 marks or nothing. Or the learner could have said, when the time of impact increases, then the net force decreases altogether. So that is 2 marks. Right, I hope you are able to do that, because there it has to do with that relationship between net force as well as the contact time. Good. Then we go to the next question. Right, this question was obtained from a Free State question paper. Right, a trial examination question paper. Now we are being given a question here, or rather a scenario. A hunting rifle of 3.6 kilograms fires a bullet with a mass of 8.4 grams. The bullet leaves the barrel of the rifle at a speed of 914 meters per second, which is 914 meters per second. Now, let us analyze this particular situation. This situation we can deal with before the firing as well as after the firing altogether. So before the firing, you will then agree with me that the rifle itself was stationary. The bullet was still within the rifle, so it was stationary. But after the firing, then you will agree with me that the bullet was moving, so it was moving to the right. And we know that this rifle will recoil, it will go back, and therefore it will go back at a particular velocity. Now, 3.1.1 says, when we deal with the principle of conservation of momentum, we refer to an isolated system. Then we are asked, what does isolated system mean? By now we know that an isolated system is a system whereby the net external force acting on the system is equal to 0. It's a system whereby the net external force acting on the system is equal to 0. Now let us see how we mark that one altogether. Then we just say the net external force acting on the system is 0. That is what we mean when we talk about an isolated system. So you can see that it's 2 marks or nothing. It means everything must be correct in order for you to get your 2 marks. Then we go to the next question. We are asked to calculate the velocity of the rifle at the instant the shot is fired. So we are actually looking at the velocity after the firing has taken place. We know that before the rifle was stationary, the bullet on the inside was also stationary altogether. But after the firing, then we know that the bullet will be moving at 914 meters per second, and that value makes sense because we are dealing with what? With a bullet, and it moves very fast. But we know that the rifle is definitely going to recoil and it will move to the left. So we want to know the velocity with which it's going to move when it recoils, meaning after the firing. Then we say the sum of the initial momentum before the firing is equal to the sum of the final momentum after the firing. Then we break it down, we get a mark, we break it down. Remember now, both of them were stationary, and because both of them were stationary, it means the initial velocity here can be taken out as a common factor. So this is the initial velocity, this one, that has been taken out as a common factor. And this will then be the mass of the rifle plus the mass of the bullet. And we know it is the same because we have taken down or taken out the initial velocity as a common factor. Then it's equal to, after the collision, remember this collision now, we have the mass of the rifle and the final velocity of the rifle, and then the mass of the bullet, the final velocity of the bullet. Then we do our substitution. Now, when we do our substitution, then the mass of the rifle is 3.6 kilograms, so it was already in kilograms. And then the mass of the bullet, remember, it was 8.4 grams, so we must divide by 1,000 altogether. So when we divide by 1,000, then it goes to kilograms. So it's actually 0.084 kilograms altogether. So you just go to your calculator and then you take 8.4 and you divide it by 1,000. So it gives you 0.0084. So there, it just doesn't show nicely. You must actually have a 0 there. So it's 0.0084, and this is now in kilograms. And this will be equal to, after the firing, the mass of the rifle is 3.6, and then the final velocity we do not know, plus the mass of the bullet, it's still 0.0084 multiplied by the final velocity of the bullet, which is 914. Now, the 914, we can see that it is positive. Why? Because we said the direction of the bullet must be positive. And simply put, right, you can easily just say, because we see the bullet is going to the right, so we are basically saying the right is positive. Then you work out this, you will see that you get negative 2.13 meters per second, and therefore the final velocity of the rifle is 2.13 meters per second, and it must be to the left. So 1 mark was for the formula, 1 mark was for the substitution of the total momentum before the firing. The 1 mark was for the everything being correct for the total momentum after the firing. And the final mark, can you see there, my dear learners, it was for both the magnitude as well as the direction. It means if any of those is incorrect, then you cannot get a mark. Or if you just give us the magnitude, then you don't get a mark. Why don't you get a mark? Because we've been told that we need to calculate the velocity. And when we get the velocity, because it's a vector, then we will give both magnitude and direction. Now, they are asking us, will the magnitude of the velocity of the rifle be greater than, the same as, or less if a heavier bullet is fired at the same velocity with the same rifle? Now, obviously, if it is the same, everything is kept the same, but the bullet is heavier. Now, when the bullet is being fired, then it will exert a bigger or a greater force to the left on the rifle. So the force that will be acting to the left on the rifle is going to be greater. And when it becomes greater, then the velocity with which the rifle is going to recoil with, meaning the velocity with which it will move to the left with, is also going to be greater. So our answer there must be greater than. Then we are asked, is this collision elastic or inelastic? Now, before we can even answer this question, let us remind ourselves, what do we mean when we say a collision is elastic? And what do we mean when we say a collision is inelastic? And by definition, if we ask you, an elastic collision is a collision in which the total linear momentum is conserved and the total kinetic energy is conserved. If the collision is inelastic, the total linear momentum is conserved, but the total kinetic energy is not conserved. What does this mean? Let us just quickly talk about elastic collision. It then tells me the total linear momentum is conserved and the total kinetic energy is conserved. So it means the total linear momentum before the collision will be equal to the total linear momentum after the collision. If it is elastic again, the total kinetic energy before the collision will be equal to the total kinetic energy after the collision. But if the collision is inelastic, then the total linear momentum is still conserved, just like with elastic. So the total linear momentum before the collision will be equal to the total linear momentum after the collision. But if the collision is inelastic, then the total kinetic energy before the collision will not be equal to the total kinetic energy after the collision altogether. Now, definitely, we know that this particular collision is inelastic because the total kinetic energy before the collision will not be equal to the total kinetic energy after the collision. Why are we saying that? Remember, before the collision or before the firing, you will then understand that both the rifle as well as the bullet were stationary. So the total kinetic energy before the collision or before the firing was 0 joules. But after the collision, or rather after the firing as well, then the bullet had a particular kinetic energy and the rifle also had a particular kinetic energy, which is not 0. And therefore, the total kinetic energy before the collision, before the firing, is not equal to the total kinetic energy after the collision. Now, in 3.1.5, they say give a reason for your answer to question 3.1. 1.4 and support your resonance with the necessary calculation. So our reason there is, it is an inelastic collision because the total linear momentum is conserved, but the total kinetic energy is not conserved. And the main reasoning is basically on the total kinetic energy not being conserved. And now we must support our answer with the necessary calculations. In other words, we must deal with calculations on kinetic energy. Then we go. Total kinetic energy before the collision, we calculate it separately. So the total kinetic energy before the collision will be the kinetic energy of the rifle plus the kinetic energy of the bullet. And we know this is actually the kinetic energy of the rifle, and this is the kinetic energy of the bullet all together. Now, kinetic energy, when you go to your formula sheet, you know it's given by half mv squared. The kinetic energy there is also given by half mv squared. So we will then say, in our substitution, it will be half multiplied by the mass of the rifle. Remember, it was 3.6 kilograms. And the initial velocity of the rifle, remember, it is 0 meters per second. Why? Because the rifle was stationary. But when we add it to the kinetic energy of the bullet, then we say it's half multiplied by the mass of the bullet. Remember, it was in grams, so we converted to kilograms. So we divided by 1,000, and hence we got 0.0084 kilograms multiplied by the initial velocity there. It's 0 because the bullet was also stationary. Are we together? And then you do your mathematics there, your answer then gives you 0 joules. So we calculate it separately. Then we go again, we get the total kinetic energy after the collision. So EK is equal to still the kinetic energy of the rifle and the kinetic energy of the bullet. And this is after the collision, which is after the firing. So after the firing, this is half mvf squared plus half mvf squared, but this is for the rifle, that is for the bullet. So it will be half multiplied by the mass, which is 3.6 for the rifle. And after the collision, remember now, this the velocity was 2.13 meters per second, and remember we need to square that one. But remember here, my dear learners, we don't substitute direction, because now when we actually right. So when we actually substitute our velocity there, my dear learners, we don't really give direction. And the main reason there, my dear learners, is that this is actually speed, because we are now dealing with kinetic energy. We are now dealing with kinetic energy, which is a scalar quantity. So we actually then take it that the velocity is equal to the speed. And hence we don't substitute the negative there. So it becomes 2.13 squared. Plus, now we go to the kinetic energy of the bullet after the collision. And that will be half multiplied by the mass of the bullet. Remember, it's 0.0084 kilograms. Multiplied by, remember, after the collision, or remember after the firing, the bullet was moving at 914 meters per second. And remember now we have to square it. And the only value that we are squaring there is the square of, we are only squaring the value of the velocity, which is actually equal to the speed and squared. And hence we don't really substitute direction there because our velocity at this point is equivalent to the speed. And our answer there gives us 3,516.83 joules. Remember, joules, my dear learners, must be a capital letter J, and that is the unit that we use for kinetic energy. Now, we are not done there because they did not ask us to calculate the total kinetic energy before the collision and the total kinetic energy after the collision. They wanted us to prove and using a calculation and give a reason. And we have done our calculation. So when we reason why we actually said in question 3.1.4, why this collision is inelastic is because the total kinetic energy before the firing or before the collision is not equal to the total kinetic energy after the collision, or rather after the firing. And that is how you obtain your 4 marks altogether. So 1 mark is for both the formulas being correct for kinetic energy in any of these calculations. 1 mark is for the entire substitution being correct. Now, what are you learning from this, my dear learners? To say you need to be accurate because it's not just a mark there or a mark there. It's everything being correct for 1 mark. Then the entire substitution again being correct, you get 1 mark. Then for completely answering what they asked you, which is the reason that you were supposed to give as to why you said in 3.1.4 this particular collision is inelastic, then you would then say the total kinetic energy before the collision is not equal to the total kinetic energy after the collision. And you can clearly see that because before the collision it was 0 joules, but after the collision it is 3,516.83 joules. So let us be able to answer the question. And the question actually ends with that particular statement. So this is how you present your answer in order to be able to obtain full marks. Right, so that was a very nice question actually. Then we move to the last question for today. Now, this question is independent of the questions from 3.1.1 to 3.1.5 because it is now talking to a soccer ball. It reads as follows. A soccer ball with a mass of 400 grams moves across a horizontal floor in a straight line at a speed of 4 meters per second. It hits a wall and then moves in the opposite direction at 3 meters per second, directly after the collision. The ball is in contact with the wall for 0.14 seconds. Calculate the magnitude of the force that the wall exerts on the ball. Now, dear learners, let us analyze what is happening here. We have a soccer ball. We've been given the mass there, and they said the mass is 400 grams. Automatically, I know that I then need to take this value of 400 grams of the mass to kilograms if I am to use it in calculations. And it is moving across the horizontal floor at a in a straight line at a speed of 4 meters per second. Remember, it was going towards the wall. Now, this definitely represents the initial velocity. Why is it the initial velocity? Because it is the velocity before it hits the wall. Can you see what I have done there, my dear learners? I have read the question the first time. The second time, I'm analyzing the question to see what is actually happening so that I'm able to allocate variables or quantities to the values that are given there. And you can basically say there it was going in the original direction, because we actually haven't been given a diagram in this particular question. It hits a wall and then it moves in the opposite direction at 3 meters per second. So this is the velocity after it hit the wall. In other words, this value represents the final velocity because it is the velocity after the collision. Then the ball is in contact with the wall for 0.14 seconds. In other words, that represents the contact time. Remember, my dear learners, when there is a collision, there is a net force that is acting on the wall, and there is still a net force that is acting on the soccer ball altogether. And the time it takes that net force to act on the wall as well as the ball, we refer to that as the contact time altogether. Then we are required to calculate the magnitude of the force that the wall exerts on the ball. So it must be the force that is acting on the ball. Why is it important that we understand that? Because the direction of the force is going to be important altogether. And we need to then use values of the ball because we are interested in the force that is acting on the ball. And nicely so, we are required to get the magnitude. Are we clear? In other words, even if we don't show direction, then we'll still get a mark. Now, this is what I also want to show you, my dear learners. When we started with this question in 3.1, we were given a diagram altogether, and we were able to answer the questions that follow. And we made sure that the information that was there corresponds with what we see on the diagram. But check further when the question goes on. You have not been given the diagram. In other words, you must be able to create the diagram for yourself, and that's what we also want you to practice. Now, let us say there. Okay, just quickly getting an eraser. Right? I want a straight wall. Right, that's much better. So let us say this is your wall. And here you have a soccer ball. Okay, should actually, okay, it's fine. Now our soccer ball is actually going towards the wall altogether. And as it goes towards the wall, it is going with an initial velocity of 4 meters per second. And then after hitting the wall, then it goes in that direction. And now that one is 3 meters per second, right? So if we were interested in the direction as well, a learner could say towards the wall is positive, away from the wall is negative. So let us take different directions. It's really up to you. You could say towards the wall is positive and away from the wall it's negative. Now let us get the magnitude of the force. Now before we even go further, another learner could say, I'm looking for F net, and I've been given the value of delta t, and I can actually get the change in momentum. And why can I get the change in momentum? Because I know the change in momentum is actually mvf minus mvi altogether. In other words, if we broke this formula down further, we would have said F net multiplied by delta T, which is still this side, is equal to MVF minus MVI. Why? Because MVF minus MVI is actually what we see as the change in momentum. You know that, right? Yes, you do, because in your formula sheet, you have delta P showing you as being equal to MVF minus MVI. Right, there we go. Minus MVI. So you can definitely see that, oh, this is a formula for changing momentum, and this changing momentum is MVF minus MVI. So when you go to this formula where you see delta P, then you can have MVF minus MVI. Now, according to this, we have all the values. We are looking for F net, we have delta T, we have the mass, we have VF, we have the mass, we have VI. So the only thing left is to do our substitution, then we will get F net. Now, what am I trying to teach you here? I'm just trying to teach you, my dear learners, that when you allocate quantities, physical quantities to the values that you've been given, you can actually see a relevant formula that is going to help you to answer the question. So, towards the wall, let us say it is positive. Then we know that this formula there, it has just been rearranged, and it's that original formula there that says F net delta T is definitely equal to delta P. So there it is just rearranged to say F net is actually equal to delta P over delta T. But you don't need to rearrange it. You just work it out at the end, which is the F net that you are looking for. So if we know that F net is delta P over delta T, then we break it down further, then we'll say F net is equal to, remember delta P is MVF minus MVI divided by delta T. This is going to be equal to, remember the mass was 400 grams. So if it is 400 grams, it means I need to take it to kilograms. So I need to divide that 400 grams by 1,000, and it will be 0.4 kilograms, because remember our formula wants us to substitute the mass in kilograms. So we'll have 0.4 kilograms into the final velocity is 3 meters per second, right? Remember final velocity, that is when it was going away from the wall. Now, if we said towards the wall is positive, it means away from the wall it's negative. So that velocity will be substituted as a negative value. Minus, remember this minus comes from the formula. The initial velocity was 4 meters per second, and that is when it was going towards the wall. And hence I substituted that value there as a 4. Divided by the contact time, remember, with the wall it was 0.14 seconds. Then we get our answer to be equal to negative 20 newtons. And then we can't leave our vector as negative. Then we say the magnitude then of the F net is equal to 20 newtons altogether. Now, if you leave that value as a negative, then we cannot give you a mark there altogether, because you cannot leave a vector negative. So you need to go and do that and basically write down your vector as a positive value. And intentionally, I chose this question for you because I want you to remember that these are some of the mistakes that I'm really expecting you not to do going forward altogether. So we have dealt with two very long questions actually, but I really hope that you have learned something, because you know they brought us all forms of calculations that you can actually expect in terms of momentum and impulse, and also to highlight to you how we mark and the mistakes that I'm really hoping that you will not do, so that you are able to get your level 7s. Now, I have definitely enjoyed the lesson, and I hope you have done so too, and I'm going to see you tomorrow for our question and answer session altogether. But before we go, just for preparation of the examination, for those that are not aware, this topic will be plus minus 22 marks in paper 1, and it is very important, and you can actually collect all the marks. So thoroughly prepare for this one. The questions, you will have less in multiple choice questions, but you will have a lot of these questions in your structured questions. So thank you very much. I hope that you have definitely enjoyed this lesson. I will see you tomorrow at 12:30 for our question and answer session. If you have any questions, remember you can forward them today, at least to this particular email address, which is stemdigitalschool@africateengeeks.co.za. When I receive your questions, I will definitely be able to assist you with those tomorrow. Thank you for tuning in, and goodbye.